Okay, so chapter 2. Okay, so statistical learning. And mostly this chapter is about regression analysis. Okay, so example. So we want to increase the sales of a product by increasing the advertisement. So we have the data for sales and the budgets for the TV advertisement and the radio advertisement and the newspaper advertisement for 200 market. And we have data. So we want to see which advertisement budget should we increase to increase the sales. So this is the figure. So we have sales on vertical scale and the advertisement on the horizontal scale. So this is just a pairwise plot of the TV and the sales and radio and the sales and the newspaper and the sales. So the data, the original data should look like the sales, maybe the sales and the TV and the radio and newspaper. And we have the 200 observations. Then we have some amount. The sales is the $20 million. And the TV is 105, and the radio, the 25, and the newspaper 55, and so on. So we have this kind of data. So, but we only see the pairwise plot. For example, the first pane is the sales against TV. So we just use these two columns to make the data. Okay, so you can see that the higher advertisement amount means the more sales. I don't know, it's causation or just relationship, but at least we have some positive correlation between the TV advertisement and the sales. And the radio and the sales, maybe the relationship is less clear, but still we can see the more advertisement, the sales tends to be higher. Newspaper even vaguer, but still probably that we have some positive trend. So this is a regression line. So I don't know how reliable the slope is, but still the larger. So in this case, the model is this. So Y is sales. And the X is, for example, the TV. So to determine alpha I, if we determine alpha I and beta I, then we can see the relationship between Y and the X sub I for a specific I. So we have 3 different models. Okay. So this is the simple linear regression. Yeah, so in general, we can construct the more complicated model. And I think that you have studied the multiple linear regression, right? So anyone have not studied multiple linear regression yet? Only simple linear regression? Yeah, Stat 2210 only covers simple. Okay, so it sounds that everyone have studied the multiple linear regression. And in this case, maybe Y is the linear combination of the intercept and the X1, X2, and X3. So here, the X1 maybe TV, X2 is radio, and X3 is newspaper. Yeah, so here the objective is to estimate beta naught, beta 1, beta 2, and beta 3. So even if, for example, the beta 3 in the previous slide is significant, possibly this beta 3 may not be significant, because if we know the TV advertisement amount and the radio advertisement amount, then newspaper isn't really a significant factor. So that is possible case. And if we estimate these ones, then we write this as the beta hat I. So hat means estimated. So the beta I this is the constant. So this is just number. But this is estimated by x1 to xn. So this is random. This is estimated from the observations, 200 observations. So that means estimate depends on the observations, and observations are random. So the estimate is also random. And more generally, that we think about this model, maybe x1 times x2 matters for y. So if someone see the product in both TV and also the radio, then maybe more people are willing to buy that product. So in such a case, maybe x1, x2, the product of x1, x2 that has some positive coefficient. Or if it doesn't matter, so if those consumers see the product somewhere, then anyway, they will buy it, then maybe the coefficient of x1 times x2 may be negative. So that is also possible case. Or maybe the beta 4, or maybe we have the quadratic term. So the x1 square matters. Or maybe another case is that even if you increase the TV advertisement too much, then it does not affect the sales. In such a case, maybe x1 square root does matter for the results. So it really depends. So in general, we have the function of x1, x2, and x3, and we have infinitely many possibilities. And in general, we write the estimate for f as f hat. Yeah, and conventionally, these x are regarded as the deterministic, and the epsilon is random, and y is random. So you can see that for example, here, only random terms are here and here. Okay, so x and betas are deterministic. So x is given, the predictors. So the x is deterministic, and the beta naught, beta 1, beta 2, beta 3, these are parameters. So in frequentist approach, these are constants. So in more advanced scheme, sometimes x is also random. We have measurement error in the advertisement amount, or even in the Bayesian scheme, even the parameters are random. But in frequentist approach, in traditional approach, the y and the epsilon are random. The others are deterministic. Do you have questions so far? Yeah, so this is kind of the machine learning course. So that we would like to modify the model so that we predict y better. So not only multiple linear regression, but we think about more general function. Y is f of x1, x2, x3 plus epsilon. Yeah, so we have several the objectives here. So one is to predict, to forecast the y, the better, using x1, x2, x3. So to be exact, when we have a new observation and that we have the TV advertisement, radio, and the newspaper advertisement amount, then we would like to forecast the y value for this new observation, maybe 201st observation. Yeah, so the estimate y hat is denoted as the f hat of x1, x2, x3. Yeah, so these three variables. So maybe we have 200 observations beforehand. So maybe I would say that x1, x2, x3 are available for 200 observations. So that means that originally that we have available observations x1 100, x2 100, x3 100, and originally we have the advertisement amount, so y1 to y100. Okay, so now we have another observation, so new observation x1, x2, x3. Maybe sorry, maybe we have 200, right? So 200 observations originally. So we have originally this data set. So this is the original data set, the training data set. Then we have the new observations. Then we would like to predict the y. So, and if we use the estimated f, then we can plug in numbers x1, x2, x3 to get the estimate for y. And another interest is inference. The statisticians traditionally they focus more on inference. So estimate the size of beta. So this is slightly different from the previous one because in the previous slide, basically, I mean, for forecasting, basically our objective is to get y hat, more accurate y hat. So beta I is just intermediate product. But in inference, we would like to see what's the slope when we increase the TV advertisement amount by $1. How much does sales increase? So we would like to know that. And also, we would like to test if beta I is equal to 0. If beta I is not significantly positive, then maybe companies want to abandon that advertisement channel. Yeah, so the machine learning focus more on forecasting, but the traditionally statistics deal with inference more. Or, for example, the economists, they would like to know more about the testing beta I or estimating beta I. Yeah, you can stop me at any time if you have questions. Okay. And to get the more accurate the forecast, we need some criterion. And the most common criterion is this, the mean square error. So suppose that we have observations x1, y1 to xn, yn. So here, x1 may be a vector. So maybe x11 to x31. Okay, so maybe a vector. Okay, so we have maybe TV and the radio and so on. Oh, sorry, someone entering the. Okay. Yep. Okay. Yep. So yeah, so xi may be a vector. So suppose that we have observations x1, y1 to xn, yn, and and the predicted values are yi hat for ith observation. Then the mean square error is defined by this. So basically, the sum of squared errors and then divide by the sample size. So this is a kind of the mean of the squared error. So we say mean square error. So sometimes we use the root mean square error. So root. Then we take square root. So the reason is that the unit. So suppose the y is in dollar. Then what's the unit for MSE? You can see that the yi minus yi hat. So this is the squared quantity. So the unit is the squared dollar. That does not make sense, right? So that's why often the people want to take this the square root of mean square error. So RMSE. Yeah. And the MSE is the sample version of the expected the size of squared error. So this expectation, and the sample version is this. Maybe some people want to divide this by n-1, but basically this is used to compare the forecasting performance. So always divided by n or always divided by n-1. Anyway, the relative size does not change. So just for simplicity, that we divide by n. And why we use the squared error? For example, why not using absolute value of yi hat minus yi? So it really depends on our objective. Oh, go ahead.
No. Continue.
Oh, okay. Yeah. So the So the reason is that this MSE corresponds to likelihood function if the errors are normal. if error term is normal. So remember that the normal distribution, the normal density is f of epsilon is equal to the 1 over square root of 2 pi sigma square. I mean the sigma, maybe if we put outside of square root, then exponential, the e to the power negative epsilon square over 2, and take logarithm. Then, so this is some constant term, maybe log of something. Maybe 1/2 times log of 2 pi sigma square, and minus epsilon square over 2. So the first term is constant. So the point is this epsilon square. So the log likelihood is basically negative of the squared error. So this square and this square corresponds to each other. So that is primary reason that we often use the root mean square error. But basically the error is distance between data and our estimate. And the distance is usually measured by the sum of squared quantities, right? So Euclidean theorem indicates this formula. So this is the most common technique. For example, in a Kaggle data competition, often the required measure of error is the root mean square error. Okay, have you heard of root mean square error?
Yes, we have heard of that.
Okay, yeah. So sometimes we just say the likelihood or something, but yeah. Okay, so that's it. And the next one. Yeah, so I think that this is a little new concept if you have just taken 5030 or 5800. So reducible error and irreducible errors. So yeah, for example, the just the predicted temperature tomorrow at noon. So if you have the all kind of you know atmospheric knowledge, and then you have a better estimate, but you cannot be 100% accurate because of the noise. So we have the reducible part and irreducible part in errors. And okay, so at first we assume that the epsilons are independent for different observations. So we have the 200 observations in the previous example, but the 200 observations are independent. And if we have a new observation in a new market, then that observation is also independent with the existing 200 observations. Okay, then what's the reducible and the irreducible errors? Okay, so suppose observations are here, xn and yn. Particularly xn is the trivariate. Then, okay, so expected error. Expected error is the expectation of the square of y minus y hat. The y is observation and the y hat is estimate. Okay, so this is the actual observation, actual, and this is predicted. Okay, so we try to decompose this. And y is, by definition, the f of x plus epsilon. And the y hat is, okay, estimated by f hat. That's the same meaning. Then we decompose this. So, okay, so f of x, this is the constant, right? So x is constant and f is a function of beta and x. So this is constant. And epsilon is new observation. And f hat is based on estimate. So this depends on x1 to, sorry, maybe I would say that the y1 to y100, yn. Okay, so x is anyway deterministic, so y1 to yn. So you can see that these components are independent. Constant is anyway independent from anything, so constant, and a new observation. And the training observations. So these are independent. In the previous example, the 200 observations are in the last part, and we would like to make a forecasting for the 201st observation. So these are independent. So these are independent. So that means the expectation decompose. So suppose A and B are random variable, then expectation of AB is expectation of A times expectation of B if A and B are independent. Right. So actually the cross term cancels, and also we would like to note that the expectation of epsilon is 0. Error is 0. Error is centered at 0. So that's why we say this as error. Otherwise, this is a bias. Okay, so then we can decompose it. So this is, okay, so maybe I would say that the f of x minus f hat of x. So this is the one component, and the epsilon is another component. Then the first term, the square of first term, and the square of epsilon, and the cross term, epsilon and this. But the epsilon and the f hat is independent. So you can decompose this. Expectation of epsilon times expectation of f of x minus f hat of x. But the expectation of epsilon is 0. So this disappears. So we only have two terms. So the first term gets smaller if f hat is more accurate. So f hat is almost similar to f, then it becomes smaller and smaller. So one is specification. If you have the correct model, then f hat is close to f. And also, if we have a larger sample size, the f hat is closer to f. But the second term does not change so whatever you chose. So f hat doesn't matter for this term. So this is a kind of intrinsic error. So this is called irreducible error. And the first term is called reducible error. So our objective is to make reducible error smaller. So irreducible error, we cannot control. So basically the variance of epsilon square is controlled by other factors, other than TV, radio, and newspaper, maybe temperature or general business conditions or some other factors. And the statisticians put it as a random error. Questions? Okay, so reducible part and irreducible part. So even if you do best, still the error cannot be 0. Yeah, so this part is reducible error and this part irreducible error. Yeah, so we discussed the view of statisticians, but why have some factors such as temperature or business cycle or rival company's product, so that we cannot entirely make the accurate prediction model. So anyway, we have some errors. We have very limited information, so we cannot avoid some error. Yeah. And the next one is the model. So we have discussed the multiple linear regression model. So this is so-called a parametric model. So in the sense that we only have the finite number of parameter, beta naught, beta 1, beta 2, and beta 3. And basically this is the 4 numbers. So 4 numbers that describe the model. So if this number is fixed and finite, we say the model is parametric. So even if we increase the sample size into 500 or 1000, still we only have 4 parameters. So this is the fixed number. So this is called a parametric model. And the non-parametric method. So this does not depend on the finite number of parameters. So for example, y hat is defined by the mean y value of the 5 nearest observations among x1 to x, sorry, the x1, y1 to x, and yn. then this is non-parametric. So it does not depend on the specific number of parameters, right? So this is somewhat useful. So if you want to predict, for example, that you are some test result or something, then you will pick the 5 very similar students to you, maybe the same, the academic record, the same course you have taken with those students, and then maybe you are in maybe the similar age to the those students, and you just narrow down the very similar group, similar cohort, then you can predict the your maybe score the better, right? So this is a kind of the non-parametric method. So basically, for each observation that you have to choose maybe the 5 nearest observations. So it does not depend on specific the fixed number of parameters. Yeah. Yes. So that we have the parametric methods and the non-parametric methods. So parametric methods have more interpretation, right? So the how much the TV advertisement matters for sales. But the non-parametric method is more data-oriented. So it's more flexible, but there are not much philosophy behind it in terms of the real implication. Yeah. Any of you has already studied non-parametric methods in the past in other courses?
Yeah, I have.
Okay, in which course?
I just studied it on my own a bit.
Okay.
Like k-nearest neighbors, like trees and stuff like that, right?
Yeah, k-nearest neighbors. Yeah, yes, and the tree methods.
Like bagging, boosting.
It can be parametric. It can be parametric, and yeah, it can be non-parametric. But yeah, originally that's parametric model. But,
oh, really? I thought it'd be non-parametric.
So it really depends, right? So even the linear regression, if we have only 4 fixed number of parameters, then this is parametric methods. But suppose we have n observations and we choose the best square root of n parameters, then the number isn't constant, right? So in that case, we say this is non-parametric method. So yeah, okay. So any model can be non-parametric, but yes, the tree method can be parametric, because, for example, if the entire predictor space is here and we only allow the 2 separation, then area A and B and C, then it can be described as the finite number of parameters. So we can say this is parametric. Of course, estimation is more complicated than linear regression, even if we have very simple tree. Yes. Yeah, okay. Yeah, so any method can be parametric and non-parametric. And the parametric means the fixed number of parameters. So if the number of parameters depends on n, then we don't say parametric. Okay, any others? Have you ever studied non-parametric methods for regression?
Where n's the number of observations, right?
Yes, n is number of observations.
Well, so like for k nearest neighbors, you choose the k, right?
That's right. So k is fixed, but still the rule, they cannot be described by the simple number of parameters, right? So yeah, so nearest neighbors, we choose, for example, 5. This 5 is constant, that's true. But it does not give this kind of the specific formula based on x1 to x500, x1 to xn, right? So you have to choose 5 observations, and those 5 observations really depends on the new observation.
Okay.
Yeah, think about the computer code. So 5 nearest neighborhood method, then if you write the code, then actually just a fixed number of parameters, you cannot really express the formula. Right. if 100 observations and 100 nearest observations, then just that is average. So we can describe without any parameter. But in the case of 5 nearest neighborhood, then we cannot, right? Yeah, that's it. So think about the maybe, okay, so to understand the situation, think about the 1 nearest neighborhood method. Okay, so then we have to choose the nearest observation, right? And we have the 100, the existing observations, and the coefficient that changes depending on the value of x, right? So that means we have some indicator functions, and we need actually the 100 parameters we need. And this is a more maybe philosophical thing, but the more complicated model is often hard to justify. So suppose we want to explain the weight of the shell by the diameter of the shell, and we think about the 2 formulas. So one is y is equal to constant times x cubed, and the other is y is equal to alpha times x to the power 2.1. And suppose the second one is better in terms of the MSE, but the 2.1 is really hard to justify. The cube is really easy to justify because the shell is 3-dimensional object. I think I would like to start the new poll. I'm not sure if it works or not, probably no. Which model is better? Y is equal to a times x to the power 2.1 or alpha maybe a times x cubed? Actually, this doesn't work. Maybe you can just speak up. So what do you think? Which is better, the x to the 2.1st power or 3rd power? Suppose the first one, the x to the 2.1, has smaller training error size. Anyone?
I'm a little confused on what this means. Interpretability, is that how like readable it is, or is that how well it'll do on non-trained data?
So the interpretable means that we have more scientific justification.
I would say that the first model is more interpretable because it fits with like the
data.
3, yeah, with the data and with how the data actually feeds into what you're trying to explain. Whereas if you were trying to talk about the second model, what is x to the 2.1? It doesn't match up with the physical reality of what you're talking about. So it might be less clear to use as an explanatory
which
model.
one do you support? 2.1 or 3?
The first one, the 3.
2.1.
No, the 3. I think, yeah. In terms of
3,
interpretability, I think the first one.
In terms of interpretability, yes, that's right.
Yes, makes sense.
Any other opinions?
I would say that the model with the 2.1 would be a better model. Mostly because like if we're looking at the error, it has like a lower error. So I thought like possibly it would be better to favor the model that has a smaller error.
I see. So actually the Catherine's opinion and Jacob's opinions are both correct, and there's no consensus behind it. So if we put more emphasis on data, we will choose 2.1. But if you're a scientist and we cannot really justify 2.1, then you may opt for 3. So it really depends. Probably, machine learning engineer or maybe data scientists maybe choose 2.1 more often, and the scientists in the biology or something may tend to choose the 3x the cube more often. So it really depends. So I don't know. Sometimes 2.1 is not acceptable for some scientists. So no consensus. Yeah, I personally, want to rely on the data, so 2.1, but I also understand that that is not acceptable in some context. So the body mass index is the height square times constant is equal to weight. Sorry, the weight divided by height square is the body mass index. So they used square. So the square still maybe there's some people, justify it because basically, I don't know. So the person with the height of 1 meter and a person with a height of 2 meters are not similar, right? So the different shapes. So the square is sometimes the justifiable. 2.1 maybe less people can justify it. So yeah, it really depends on the context. Sorry, so it's a little bit vague. But for data science or machine learning context, maybe more people tend to choose 2.1. And more scientific, the more area specific context, maybe more people choose 3. So the next one, the trade-off between the flexibility and interpretability. So we have different models, and the least square method is here, so linear regression. And some methods are even less flexible, but the more interpretable. And I would say that the lasso model put even farther away. So maybe around here. So subset selection. Suppose we have 100 candidates of predictors, then we choose only 3 predictors out of 100. So it's at least, the lower flexibility. We have the smaller number of parameters, and but the higher interpretability because we only have 3 factors. So we can explain the relationship between Y and the predictors. And the lasso is a kind of the method to artificially choose the smaller number of parameters. So subset selection, we may have maybe 3 variables, but the lasso only choose 1 or 2 variables. Or a more typical case is we have 1,000 candidates of predictors. Subset selection, we have 100 of predictors still, but the lasso only have 10 predictors or something. So maybe we should say it's more interpretable, but less flexible model. And generalized additive model, the trees is basically linear regression with separating cases. So it's more flexible, but it's a little more ad hoc. So we can set the threshold and we can divide the linear model into 2 pieces. So piecewise linear, so less interpretability. And the generalized additive model, generalized additive model is Y is equal to F1 of X1 plus F2 of X2 and so on. So we don't have the interaction between X1 and X2, but at least the function is more flexible. So, less interpretable. And more bugging, boosting, or the support vector machines. So these methods are more computational and they accommodate more flexibility, but it's almost impossible to interpret. For example, we don't have any coefficient of the predictor explicitly, so that we have the more flexible. And I would say that maybe neural network is even more flexible, maybe. I don't know where to put, but the even higher flexibility, but the less interpretability. Maybe neural networks, support vector machines, then the model is so abstract, so we cannot really see which is more flexible, but generally the better forecasting performance by neural network. So I would say this. Any questions on these slides? Okay, so maybe we can study these models later. So at that time that you can remember this slide again, then you can identify the characteristics of each model. Yeah, okay, so this is, I think, the first part of the chapter 2. And the next one, the maybe more specific context, regression versus classification. So we have two types of the supervised learning model. The one is regression, that is the quantitative response, and the second is classification, so qualitative responses. So basically we have the predictor and response. So the X is the quantitative or quantitative, maybe continuous or ordered. And Y is also quantitative. So we have the several cases. So quantitative and quantitative, both X and Y are quantitative. And X is qualitative, such as the indicator function, the male and female or species of flowers and so on. And Y is quantitative. And the X is quantitative and Y is qualitative. I mean, categorical. Maybe I would say categorical. And the categorical, X is categorical and Y is categorical. But actually the X doesn't really matter. So basically we separate the case with this, and this is the regression model. And this is the category, maybe categorical analysis or classification problem. Sorry. Regression and classification. And sometimes the second one is just, both are categorical. So the data is summarized as the table, maybe M by N table. So that we can do other things, maybe the chi-square test and so on. But basically, the X doesn't really matter, and the Y matters for modeling. Because Y is random, so if Y has different data type, then we have to prepare the totally different scheme. Yeah, so regression analysis, the quantitative, so typically real valued variable, and the classification, the binary, such as success and failure, or multi-class, such as ABC, so categories. And yes, yeah, that's it. And the classification problem is regarded as a regression problem if the category is binary, so Y is binary. And because if you only have two values, it's ordered, right? So the 0 and 1, it's ordered. So we can say that if we think about, okay, so what possible value of Y is 0 or 1, then if we think about probability of Y is equal to 1, then this is between 0 and 1, and it's kind of the continuous interval. So we can see this as the regression problem. So that is the logistic regression. Yeah, so if we have predictors x1 to xp, then we can think about, okay, so based on weight, height, and the body fat percentage and body water percentage and age, we would like to decide that person is male or female, then we can develop this model. Probability of female, the given data, as the function of the linear combination of x1 to xp. So if it's so-called link function, so you can see the inside of the quantity is real valued, but the left-hand side is between 0 and 1. The statistician regard this as in open interval 0, 1. So probability is never 0 or 1 in this case. So we have to set the function f from real numbers to 0, 1. So typically inverse logit function or the CDF function, the cumulative distribution function. Have you studied logistic regression before?
I've seen it a bit.
Yep. Others?
Yes.
And I have studied Logit model in discrete choice modeling in transportation.
Okay. Others? It's fine. So if you have taken 50-30, have you anyone have taken the 50-30 from Objet, Dr. Objet Mandal? No? Okay, so I don't know. Probably 50-30 covers logistic regression. Maybe this in some years not, but when I taught that they cover logistic regression. Okay, so yeah, so this is called logistic regression. So the difference is that we think about the probability rather than the response itself. Since we have taken the probability of the left-hand side, we don't have error term. So you can see that we don't have this error term, right? Because it's already probability, so uncertain event. So we don't have an error term. So we have F here. We don't have error here, and the left-hand side is probability, and other structure is similar to linear regression. But the estimation is more difficult. Linear regression, we can minimize the quadratic function of beta naught to beta p. Logistic regression, that we need numerical procedure. No analytical solutions. Yeah. So this is the way to how to handle the binary data by regression scheme. And the categorical response, such as A, B, or C, still that we can extend this method, but also that we have totally different method. And the regression against classification. And okay, so next we think about the case that the predictors are qualitative. And I would like to explain why it doesn't really matter. Okay, so example. So we want to explain the house sales price. So this is continuous. So the numeric, so quantitative. And by square footage and age and the architectural style. And the square footage, okay, so this is say X1. This is quantitative. Age, X2. This is again quantitative, but the architectural style is the qualitative. Okay, either ranch, bungalow, or colonial. So in this case, what should we do? So just what we have to do is to set up so-called dummy variables. So we have three types. Okay, so baseline, okay, so suppose the ranch as baseline, then we set up the indicator variable for bungalow and the colonial. So ranch, basically we have the here and here. First and fourth observations are ranch houses. And the fifth observations are bungalow house. So we just define this as 1 and the other as 0. And if we put this, maybe I would say X3 here, maybe, and the X4 here, then X3 represents how much the bungalow house, I mean the price of bungalow house compared to the price of the ranch house on average. So if the coefficient of X3 is 1,000 in dollar, then that means the bungalow house is $1,000 higher than the ranch house on average if we have accounted for square footage and age already. So if we have the same square footage and age, then bungalow house is $1,000 higher. So in such a case, the coefficient of X3 becomes 1,000. And the same for colonial. So if we have the three categories, basically we have to set up the two indicator variables, two dummy variables. Then we can fit the regression model in the same way as usual linear regression model. So formally, we have the four predictors: the square footage, age, dummy variable for bungalow, and the dummy variable for colonial. So in this way, qualitative categorical variables that can be interpreted as numeric variables.
Are dummy variables the same thing as one-hot encoding?
Sorry?
Are dummy variables the same thing as a one-hot encoding or making a one-hot vector?
One-hot?
Maybe I'm saying it wrong. Let me Google it. Sorry.
So sorry. What did you say? So dummy variable is the same as?
I was asking if it's the same as when you do one-hot encoding, where you take like a list of names and convert them into just like 5 different 0 and 1 variables.
Oh yeah,
do you know
yeah,
what I'm
5
talking about?
different. Yes, that's right. That's right. So just the point is that if you prepare 3 variables, then these 3 variables becomes linearly dependent, right? So if we add these 3 variables, this becomes 1, 1, 1, 1, 1, and linear regression model, then intercept variable is already included. So we have to exclude 1 variable, but except for that, yes, just coding the variable into 3 different 0, 1 variables. That's the same.
I'm sorry.
Yes.
Can you explain why you have to exclude 1 variable then?
Yeah. So we are thinking about linear combination, right? So the y is equal to the beta naught plus beta 1 x1, beta 2 x2, beta 3 x3, suppose, plus epsilon. Then if this variable x1 and x2 and x3 are linearly dependent, then we have infinitely many solutions. So that's why we have to keep this variable linearly independent. So to achieve that we have to delete at least 1 variable. Okay. So so maybe think about it. Sorry, just the white paper. Yeah. So suppose that the variable. Okay. So suppose that we have maybe just 5 observations, y1 to y5. Okay. And think about the case that, so we have intercept, right? So we have intercept, so beta naught 1, 1, 1, right? 1, 1, maybe 1, 1, 1, 1, 1, okay? Then if the 3 variables, the x1 and x2 and x3 are linearly dependent, then we have trouble to identify beta 1, beta 2, beta 3. So suppose that the beta 1, this variable, beta 2, this variable, and beta 3. Okay, so this is x1, x2, x3, and 0, 0, 0, 0, 1. Okay, epsilon. Then you can see, for example, the beta 1 is equal to 1, beta 2 is equal to 1, and beta 3 is equal to 1, and beta naught is equal to 0. That model is the same as the 1, 0, 0, 0, right?
Oh, okay. I get it now. Thank you very much for going over it.
Yeah, so we have to eliminate 1 variable. Otherwise, we cannot identify parameters. Yep. Yeah, so if we have generally the k categories, then we have to set up k-1 dummy variables. Yeah, that's the thing. Yep. Yeah, and now that we go on to the 2.2, so assessing model accuracy. So we have the 2 problems, the regression problem and the classification problem. And for regression problem that we discuss in section 2.2.1 and 2.2.2, and the classification, the 2.2.3. And we studied 2 things. So the measuring the quality of fit, and the next one is bias variance trade-off. So this is important concept in chapter 2. Yeah, so at first, what's the measure to assess the error size? And we have studied the MSE, right? And if we have n observations, then we can just calculate this MSE 1 over n times summation of the squared difference between the observation and our estimate. Okay, so this is actual observation, and this is estimated, fitted. Okay. Yeah, so if we use f, then we can write this as this. Yeah, but the this is just the given for our training set. So suppose we have 200 observations for one data set, and we can calculate the so-called training MSE. But our ultimate objective is to minimize the error size for new observations. Just put aside those 200 observations, and we have the new observations, maybe 100 new market. What's the error size? So markets. That's more important. So training MSE is intuitive, but it's not the best measure, at least we can say. So we can specifically say this as training MSE. Yeah, so this is just what I said. And this is clearly, this has the clear problem, especially if the degrees, I mean, we have more parameters. We have more parameters. So think about the model such as the y is equal to beta naught plus beta 1 x, x1 plus beta 2 x2 plus epsilon. And suppose only 3 observations are available. Okay, then we have 3 parameters and 3 observations, right? So to be exact, maybe 3 observations. So y1, y2, y3, then beta naught plus the beta 1 x11 plus beta 2 x21 plus epsilon, maybe 1, and the beta naught, and the beta 1, and the x21, and sorry, x12, sorry, x12, and beta 2x22 plus epsilon 2, and plus beta 1 x13 plus beta 2x23 plus epsilon 3. Then actually we have all errors equal to 0, and this is the same as the solving just the linear equation with 3 parameters, right? So as long as these vectors, okay, maybe I would say this is times 1, times 1, times 1. And as long as these 3 vectors are linearly independent, we can just identify beta naught, beta 1, and beta 2. But that does not mean x1 and x2 explains y. Suppose y is the weight and x1 is the length of the shell and x2 is the diameter of the shell and the beta naught is constant. Then if we have 3 observations, we can determine beta naught, beta 1, beta 2 without any training error. But that does not mean, in the future, the weight of the shell is entirely explained by the height and the diameter. Right? So we have clear problem here. If we have not large number of observations and a small number of parameters, then the problem is less obvious, but at least we have some problem to use the training MSE. Yeah. So how to measure the fit? Sorry. So that's the case. And this is another graphical explanation of the same problem. So this is the data set. So these black circles are data set. You can see this, the left figure. And we would like to fit a curve to explain the tendency between x and y. Then the problem is that, so if we fit the straight line, this yellow one, Okay, then okay, so fit does not change probably if data change a little bit, but the it's not really capture the trend of the data. But on the other hand, think about this green graph. So this is really ad hoc, and it follows the data closely, but it sounds that it picks up too much noise. So if you have another data set, the so-called test data set, maybe the ziggy line that does not fit well. Probably the best model is in between. So we can see blue one, it looks better. And actually the black one is the truth. The black one is the truth. So this is the simulated data. So yeah, black curve. So the black curve is the truth. So if we use probably the quadratic curve, that is the blue curve, then the fit is the best. So green curve maybe have too many parameters. The yellow straight line, it's too simple. And in terms of training error, training MSE, more parameter. This is basically the number of parameters. So more parameters, smaller the mean square error. But if we think about another test set, so test set, maybe the new set is like this. If we use the test set to evaluate these three fitted curves, then actually the performance is the best in the middle, so blue one. So test set is basically the set of new observations. So training set is the observations which are used to fit the model. So training set, basically the old data, the test set, the new data, or existing data and the new data, right? Yeah. So the training MSE has some problem about overfitting. So if we use the training set, that we choose basically this model, so green model, so green, this green curve on the left-hand side, but that picks up too much noise. So to choose blue one, we have to use the test MSE. So consider that we have a training data set D1 and the test data set D2.
Oh, I have a question.
Oh yeah, sure.
You mentioned noise. I don't know really what do you mean by noise. You said we have more noise in that curve. What do you mean by noise here?
Yeah, so here actually we cannot really tell what is noise and what is not noise. But in this case, this is simulation. So black curve is the true trend. So the difference between the circles and the black curve is the noise.
Okay, thanks.
And basically, this green line picks up too much noise. And in real problem, we cannot see the true curve, the true black curve. So we cannot tell how large the noise is. So, but we can only recognize that the green curve isn't really smooth. So probably it's not really the true curve. So in that sense, still we can guess that the green curve has picked up too much noise. So this is simulation, it's clear. So that the black sections are noise. In the real example, we don't know the truth. So we don't have the black curve. So we cannot really tell what is noise. But since green curve is not smooth, probably it picked up too much noise. Yeah, and the test MSE, so we have the training set and the test set, and we only use the training set to fit the curve. Then we use the test set to evaluate MSE. So the MSE for the test set is called the test MSE. So test MSEs are more accurate measure of expected error. But of course, in real example, suppose we have 200 observations. If we want to divide this into D1 and D2, training set becomes smaller. So actually, it is disadvantage, right? So to fit the data, we only have 100 observations. So we have trade-off. If we use the test MSE, conceptually it's better, but we have to halve the sample size, right? And okay, so then maybe we can get the 180 observations in the training set and 220 observations for the test set. Then still 180 is comparable to 200. But the problem is that if we only have the 20 observations in the test set, the test MSE is not reliable. Just it's a kind of the lottery. So if the model is really good for those 20 specific observations, then test MSE is small. So it's a kind of gamble. And the other way around, if test set is 180, okay, so more reliable estimate for test MSE. But if we only have 20 observations to train the model, then we cannot get a good estimate for beta naught or beta 1, beta 2. So this is not also good. So we have trade-off. So conceptually, we have to use test MSE, but to do that, we have smaller sample size. So cross-validation, bootstrap, those methods improve that situation, but basically we have some trade-off. Conceptually, test MSE is better, but if we have a limited amount of data, then we have to decrease the number of the size of training set. Yeah, so this is test MSE. Yeah. Yeah, I think this is the same one. Yeah. So so this is basically the same one. I have already explained everything. Yeah, I think that we stop here, and the next time that we study the variance bias trade-off. And I will post some quizzes for today. Do you have any questions?
If we want to read the book to kind of read ahead, do you recommend just reading the next couple sections from wherever we leave off after each lecture?
Not really. I think that after the lecture, that if you wanna see the concepts in more detail, then you can read the book. So yeah, I think you don't really have to, read the book in advance.
Okay, cool. Thank you.
Yeah, sure. So does anyone want to have the breakout rooms, or just we end the lecture? Okay, maybe. Okay, so just we finish for now, and see you next Tuesday. Next Monday. Sorry. Next Monday. Sorry, the next Monday is the MLK Day, right? Hello?
Yes, it is
Yep.
a holiday.
That is next week, right?
Mm-hmm.
Yes.
Yeah, okay. So then Monday we don't have a class, but the Wednesday we will have a class. Okay, so see you next Wednesday.
Okay. Thank you, Professor.
See you then. Have a nice weekend.
Thank you. Good night.